So, we just finished calculating kinematic problems in one dimension. Today, we're going to upgrade to two dimensions. First off, we need to properly define angles. If you stick with the geographic method of doing it, yes, you have your north, then you have your east, and then in between you have your northeast, but it'll be impossible to describe something which is 10 degrees towards the east from north. All right, so that's why we have to have a different type of notation as opposed to north, east, east, northeast, and all that crazy stuff. So this is the notation that we'll use. All right. For example, in this case over here, first you got to give context. All right. It has no meaning on its own. You'll need to include a compass rose so the reader knows what defines north. There are certain maps out there where they actually tilt north on the side because reading maps is easier holding it this way than it is holding it in scroll format. All right. So yeah, define your direction, and from here there's two ways to correctly describe this angle. One of them is from north you tilt 60 degrees towards the east. That's correct. But there's also another correct answer, and it's by looking at the complementary angle of 60 degrees, which is 30 degrees. So another correct answer would be east, 30 degrees towards the north. One way of interpreting the answers of this is that the first vector describes the initial angle you're dealing with, and then the second one is which way are you tilting towards. Try out the next one on your own. Did you get the answer of either west 20 degrees south or south 70 degrees west? Spot on. All right, so vectors can be described using a scale diagram. All right, vectors always have a direction. That's what the whole arrow thing is all about. And the arrow has given a technical name called the head. And the back end, like any animal, is called the tail. The length of it does matter, because if you give it a scale, for example, let's say that the scale of this is 1 meter per second, then that length of the green vector probably represents around 4 or 5 meters per second, and the arrow points it towards some sort of eastern direction towards the south, all right, where using a protractor you can figure out the corresponding angle relative to east. So whenever you're solving resultant component-based problems, we follow the same rules as before. You take all the vectors and you connect them together from head to tail. Then your resultant vector points to the head of the last vector drawn. I think this is best described going through an example, so that's what we're going to go through next. All right, let's say we have a lovely young lady called Evelyn, and she needs to go from the guidance office to art class somewhere down here. So she heads 65 meters towards the east, then 30 meters south, 5 meters east, and then 100 meters south to get to her art class. Two questions. First, what is her total distance of travel? And number two, what is her resultant displacement? As for total distance of travel, I think it's fairly straightforward. All you have to do is just add these numbers together. If this is a word problem, make sure you follow the grasp rule. Start off with your givens. What do you know? What are you trying to look for? The formula you're going to use to solve for the problem, and then get to the answer. As straightforward as that. Again, distance is a scalar quantity. That's why you won't see an arrow on top. It doesn't exist. All right, and you can't technically subtract distances. It's like driving your car. Even if you take a U-turn, you're still burning more gasoline. All right, so you can't subtract distances. As for displacement, it's kind of like cheating and activating God mode in video games. This is the case where you're going to be walking through the walls and finding the shortest distance from beginning to end. So if we're trying to solve this problem without using a calculator, the only way of solving it is by drawing a scale diagram. And as the name implies, you need to include a scale, and don't forget to include a compass rose. That way the reader knows how to orient the sheet of paper, even though by convention, upwards is usually north. All right, so let's get started. Haha. All right, 65 meters could be represented by 65 of these units across, so 6.5 centimeters if this was a centimeter-based graph. And then the next vector you would connect from head to tail. So the tail of the first vector will connect to the head of the next vector, and you displace 3 centimeters if each of those grids was a centimeter. Then you'd go half a centimeter towards the right, and then 10 centimeters all the way down to the bottom. Resultant displacement always points to your destination. All right, a lot of students by accident point the wrong way, as in the journey back home. No, it's the path from beginning all the way to the end. So make sure that your arrow points to the bottom right, in this case over here. So you drop your ruler down and you measure out the length of this, and you get somewhere in the ballpark of 15 centimeters, and 15 centimeters will translate to 150 meters. Next, you'll pull out your protractor and you'll measure this angle here, and you'll get roughly 62 degrees. So there are two valid answers for this. The first one is either what is listed, 150 meters east, 62 degrees south, or alternatively, you could also write it down as 150 meters south, 28 degrees towards the east. Both are correct answers. Something else I should also mention about while we're still here. You'll notice that we place these square brackets around the direction, and always leave the direction at the end of your vector. All right, don't place it anywhere else. Okay, well, let's add more conceptual examples to this problem here. All right, let's say that it took Evelyn 3 minutes and 20 seconds to get to her destination. Let's calculate out her average speed and her average velocity. And interestingly enough, you're not going to arrive to the same answer. As for average speed, by definition, it's your total distance divided by time. So you have 200 meters divided by 200 seconds, and you'll get the answer of 1 meter per second. 3 sig fig divided by 3 sig fig, 3 sig fig answer. On the other hand, with regards to average velocity, by the textbook definition, average velocity is your displacement divided by time. And here's where things start to get weird. Her God mode displacement is not 200 meters. It was down to 150 meters, but it still took her 200 seconds. So you'll notice that this time around you're dividing 150 by 200, which will give you 0.75 meters per second. Don't forget that this is a vector, and with a vector, your final answer should also have a direction as well. And no, the direction does not change. Common mistake I see is that students divide the 62 degrees by 200 seconds, and then you get some weird fraction of a degree. How is that possible? If you're going this way, you'll end up over there. All right, you won't just tilt somewhere else afterwards. So leave the angle alone. All right, here's another conceptual problem. Does order matter when you add vectors together? Well, let's test that theory out. Okay, let's say we have another lovely young student here named Cassidy, where she decides to walk 2 meters towards the west, I think 14 meters towards the east, and then another 14 meters towards the west, and then another 8 meters towards the east. All right, how will that impact her final answer? If we're to try to solve this problem graphically, we need to connect everything from head to tail. So we'll just start with our first vector and make sure that first vector is connected to our starting point. Then the head of the first vector will connect to the tail of the second vector, like so. Next, we'll bring this red vector down, making sure that the tail of it is connected to the head of the previous vector. Normally these should be on top of each other, but then that makes a really messy diagram. So for my PowerPoint, I just offset them by a slight bit. That way you can clearly see how everything all adds up. Because don't forget, your resultant displacement points to where? That's right, to the head of the last vector drawn. So in this case over here, it should be pointing towards the left. Count out the spaces, and you'll find that Cassidy has displaced 6 meters from where she started. So does order really matter? Let's say we decide to change the order around. This time we're going to start with the longest vector and then go to the shortest vector. So we'll take that orange vector, somewhere up there, drag it all the way down right there. Then we'll take the tail end of the red vector and drag it to the head of the orange vector. Lastly, with the tail end of the yellow vector, we'll grab it and bring it to the head of the second vector. Our resultant displacement always points where? Correct, to the head of the last vector drawn. So make sure that it points to the end of D1. And you'll find out that you'll measure out Cassidy's displacement still at 6 meters. How about one more test? This time around, we're going to start off with the red vector, followed by the yellow vector, and finish off with the orange vector. Now, as for this setup over here, I got to place Cassidy towards the center of the number line, otherwise it's not going to fit on your screen. But that shouldn't really matter because at the end of the day, we're only concerned about displacement. Displacement will never tell you where you are. It'll just tell you how much you've changed since your last point. That's it. All right. So let's say that Cassidy now starts from a different locker. All right. So she heads towards the right 8 meters, then towards the left or towards the west by 2 meters, and then west again. Add it all up, and it'll still have a total displacement or resultant displacement of 6 meters towards the west. So I hope that answers our question. Does the order of how we added up together matter? Doesn't matter at all. So let's use that hack now. Let's go back to this previous example. All right. If order doesn't matter, that means I can shift my order of how the vectors are connected together. Let's say that now I decide to take that red vector here and make that the second vector to connect to. So I'm going to drag that all the way up there. And then the second vector will become the third vector. Hey, look at that. That cleaned up our problem quite a bit. In fact, this makes a very special type of triangle called a right angle triangle. Excellent. And with right angle triangles, we can pull out our skill sets from math, trigonometry, in solving the resultant displacement. You'll notice that this line over here, that is the hypotenuse of a right angle triangle. So therefore, we can start pulling out the Pythagorean theorem and solving this. Okay. Before we get to there, let's just do small steps at a time. Let's break everything down and add up everything all horizontally together, and then add up all the vertical parts together as well. So the way how we arrive towards this red vector here is by adding vector 1 with vector number 3. So 65 meters east plus 5 meters east will give you 70 meters towards the east. Next, let's add up these two vectors together. So D2 and D4. 30 meters south plus 100 meters south will give you 130 meters towards the south. Excellent. Now we know the total length of the red and the blue. So, old school wise, the Pythagorean theorem looks something like up there. All right, but we want to give it context to this problem over here. We're not just talking about C anymore. C will be replaced with delta dr, which is your resultant displacement. All right, and A isn't A anymore. This is your total delta dx, and this is your total delta dy. Yes, this formula looks really messy and convoluted. Don't worry, I'll show you a shortcut afterwards. All right, but let's just stick with the narrative. This is just the way how textbooks usually show this formula. So we sub everything in, and if you're not familiar with these vertical bars over here, they mean absolute value. All right, meaning to get rid of the minus sign. There's more to it than just that. In fact, if you want to know the proper definition of absolute value, it's how far a number is away from 0. It may seem silly right now, but when you take algebra and geometry, that definition will make total sense. All right. So if we go to this example over here, well, how far is 70 meters east from 0? No kidding, 70 meters. All right. Same with 130 meters south. How far is 130 meters south away from 0? 130 meters. Now we can pull out our scientific calculator, crunch through that, and we'll get our answer. And you'll see that this answer over here will be much closer to the real answer than how we did it when we were drawing it as a scale diagram. That's one of the problems about scale diagrams. If you don't line up everything just perfectly, your answer might be a bit skewed. So we are trying to direct our calculations or our solving of this problem by the methods of using calculations. All right, and I'll show you that skill set in the next episode. For now, let's just finish off this problem over here. If we want to find out the angle over here, we could either use the protractor or we could use good old SOHCAHTOA. I wouldn't recommend sine, because with sine, you're using the opposite and a rounded value. Probably not a good idea. I wouldn't use cosine either, because you have a perfect adjacent value, but the hypotenuse has been rounded, which may induce rounding error. So really, the best way of solving this angle over here is to use the least calculated segments, which is the opposite versus the adjacent. So tan inverse would be equal to this ugly looking thing over here. Again, we're going to simplify it, all right? Because when you sub the values in, we don't really care about the south or the east anymore. That's why we have these absolute symbols here to get rid of that. So in your calculator, you'll be, let's go through that together. With your calculator, you'll be doing shift tan, open bracket if your calculator doesn't do it for you automatically, 130 divided by 70, close bracket. Make sure that your calculator is set in degrees, because if it's not set in degrees, things are going to go wrong. All right, and just looking at this logically, you should have an angle greater than 45. It's a good way to just mentally prepare for the answer. And 62 degrees sounds about right. These questions are usually out of 7 marks. If you've gotten up to here, you've only gotten 6 out of the 7. All right. For that 7th final mark, you need to conclude off everything. Don't worry, you don't need a therefore statement. Just box in your final answer. That therefore, the resultant displacement as a vector is equal to, I'd probably use 2 sig fig. All right, 150 meters east, 62 degrees towards the south. Even if you give me 3 sig fig, I won't really worry too much about it. There are actually more rules with regards to how to calculate things out, and we'll cover more of those later on this year or possibly in grade 12. All right, so just to summarize how we would potentially solve this problem mathematically. You would add up all the horizontal components together. Then you add up all the vertical components together individually. If you connect them together, you're going to form a lovely right-angled triangle. With a right-angled triangle, you can solve for the hypotenuse by using the Pythagorean theorem. And for the angle, your best bet is to use inverse tangent, also known as arctan. It just minimizes the amount of rounding error, that's all. As for the formula, please refrain from using the Pythagoras formula. The reason why is because C, A, B are all relative to any arbitrary triangle. Meanwhile, with regards to our problems, we know that there's a direction involved. All right, and it's not just C anymore, you're looking for your resultant displacement. And that's why you should write down everything technically like this. Now, as for the formula can never tell you direction, and that's why you'll see that there are these vertical bars over here. All right, so you'll never know the actual direction of it, and that's why it exists there. And we've also mentioned that with regards to these measurements over here, we want to drop direction. That won't help us out in using the Pythagorean theorem. Now, this formula may seem really messy, but there's actually a faster way of writing down this formula. All right, and all you have to do is just take your thumb, lick it, and just rub off all the arrows. Because the moment you remove that arrow there, well, the vector has suddenly turned into a scalar. And with it being a scalar, we don't even need to worry about having all these ugly bars here anymore. Whoops, need that too. Okay, so that ugly looking formula you see on the screen can be simplified down to this. And how about we use this formula from now on? All right, I'm not going to use the textbook one because it just takes way too long to write everything down symbolically. We know that without an arrow, it's a scalar quantity. Also, for your inverse tan, please don't just write down opposite over adjacent. Give me context to how you drew your triangle out. All right. Now, some people will add up the horizontal followed by the vertical. Others will start off with the vertical and finish off with the horizontal. And by altering those two, yes, you could have two different possible answers. It could either look like this formula over here or the formula down below. If it's shaded in blue, it just simply means that I will provide this formula for you for any future quiz, test, or exam. All right, and if it's not shaded for you, you'll have to figure that part out yourself. So, what makes these two different? Well, how about I just briefly go through that? And if you haven't clued in, I do typically color code out my vectors, just so that I can figure things out. Because when you go to university, you may end up getting to courses where you're going to have multiple dimensions. And with that, you probably want to color code because that's the only way you can sort through all these different vectors. All right. Yeah, I actually brought in colored pens and just solved everything that way by the time I got to fourth year university. There was just way too much going on. Okay, so as for the first formula here, how would that be relevant? Well, if you have a resultant vector that looks like this, then delta dy would be opposite of it, and delta dx would be beside it. And you'll see that I always, just for my version of it, I'll always use red for my horizontal dimension and blue for my vertical dimension. And if you think about the colors of the rainbow, green is right in between, so that's why I use green as my resultant vector. Okay, so this triangle here can be solved by using this formula here, right? Because your delta dy is opposite of the angle. However, you can also interpret this problem a different way. Here's the same exact vector, but this time around I'm doing down first, followed by across. So from this version over here, you can see that my opposite is now my delta dx, and my adjacent over here is my delta dy. All right, so if you decide to connect your triangle, like the lower example here, then that's when you have to use this formula down here. Does it really matter which one you use on any future test, quiz, or exam? No, it doesn't matter. All right, just be consistent, and that's probably the best way in getting through this stuff over here. Before I finish off, I'd like to note one more thing, is that these equations over here have been correct simply because we've been doing it wrong for a good 4 decades by now. All right, calculator companies, for some strange reason, they decided to use that as the shorthand for inverse tangent. I guess it made sense, all right, in short form. However, to the -1 really means reciprocal, and you're not looking for the cotangent, all right, which would be what this definition would be. All right, so that's why the proper way of defining inverse tangent is actually arctan. I know it's archaic, but if you pull out any textbook that's 40 years plus, they will always use arctan. They wouldn't use this new shorthand notation. Just a FYI, that's all. Okay, how about we finish off with this last example? Frank the squirrel goes looking for nuts. Oh boy, let's draw a scale diagram. All right, he starts off at the base of his tree, and then he travels 50 meters north, 20 degrees towards the east. He then travels 30 meters towards the west. Finally, he sees a pleasantly attractive looking squirrel, like this one right over here, from afar, and then he dashes to woo her. Question is, what is his resultant displacement? I'd encourage you for you to try this out by drawing a scale diagram, and I hope that at the end, once you've drawn out the entire scale diagram, you end up with an answer that looks like that. Best of luck with that, and we'll solve the same exact problem mathematically in our next episode. See you then.